Hi there, this is Coach Eikrem, and welcome to our video on electron configuration. The first thing we're going to talk about is the electron cloud. And as you know, the electrons are found outside the nucleus in a region of space called the electron cloud. And up here on the right, we've got a visual to kind of give you a good idea of what that would look like. So you can see all these electrons are bouncing around somewhat chaotically around the nucleus of our atom. So we need a way to organize that and put it in such a construct that we can use it when we're doing chemistry. And so we're going to organize it in three basic organizational tools or levels, so to speak. And they're going to go from more vague down to more specific. So the first organizational level is going to be called our energy level, and it's going to be notated with an N, and N is going to be a positive integer, so 1, 2, 3, 4, 5, 6, or 7. And those also happen to be the periods on your periodic table. So we've got energy level 1, 2, 3, 4, 5, 6, and 7. Within each energy level are going to be sublevels, and those are designated by a letter S, P, D, or F. The S block, as I call it, is this block of elements right here. And it's also going to include, I cut in there, helium right over here. The next sublevel is going to be the P block, and the P block is going to be right over here. The next sublevel is going to be the D block. It's going to be right here in the middle. And the last one is going to be the F block, which is actually going to be your lanthanides and your actinides down here. And each of these sublevels is going to correspond to a certain electron cloud shape, which is called an atomic orbital. So energy levels are the most broad, then your sublevel, then your atomic orbital. The best analogy for thinking about this is like an apartment building. If I told you I was in the apartment building and to come find me, you would have no idea where I am. Am I in a kitchen? Am I in a bathroom? What floor am I on? Which apartment am I in? And the same thing is true for electrons. You have to give specific details, so to speak, almost like an address of where the electron is probably going to be. So our energy levels are going to be like the floors in the apartment building. So ground floor, first floor, second floor, third floor, etc. Then, if we go one more specific, the sublevels are going to be the apartments on the floor of that building. So S, P, D, and F would be like the 1-bedroom, the 2-bedroom, the 3-bedroom, or the 4-bedroom apartments on that building. Then your orbitals within the sublevel are going to be the rooms within that apartment: kitchen, bathroom, bedroom, closet, etc. And the electrons are the people living in the rooms. Remember, this is only going to give us a good prediction of where the electrons are located. Note that this isn't an exact location. We can't determine an exact location of each electron, so this is essentially an estimated, it's a guess. But it's based on a high probability of where it's going to be. So what do the atomic orbitals look like? If we have our energy level, then we have our sublevels, S, P, D, and F. The orbitals actually have shapes, and they are 3D. And they're a region around the nucleus. So this just kind of gives you a good idea of what they would look like. The S is a sphere, and the P is a dumbbell. And they cluster around the nucleus. And as you can see from this drawing down here on the right-hand side, this looks nothing like what the Bohr model would have you believe an atom looks like. You know, with the electrons spinning around like planets. This is more accurate, and it shows all of those regions kind of smushed together and interlaced. And within each orbital, there's a probability that you've got specific electrons found in that orbital. And remember, this is a high probability. This is about 95% chance of finding an electron in each of these specific orbitals. So each orbital can hold a maximum of 2 electrons. This is sort of like a golden rule. Do not forget it, okay? It's never going to be 3. It's always going to be a maximum of 2. And each of these sublevels, S, P, D, and F, have a certain number of orbitals. And these questions would have you ask, okay, if it contains one s orbital, how many electrons? But I prefer to think of it kind of the opposite. If I say how many electrons are in an s sublevel, then how many orbitals would I need? That's how I like to think about it. So if I'm looking at the s block right here, on any given energy level of the S block, I have 2 electrons. So for example, on energy level 2, I have 1, 2 electrons. If each orbital can hold a maximum of 2 electrons, I only need 1 orbital for S. And in each of those orbitals, I'm going to hold 2 electrons. If I look at the p level, or the p suborbital, I come over here, I've got 1, 2, 3, 4, 5, 6 electrons in my p sublevel. And if I can only hold a maximum of 2 electrons in each one, and I have 6, I have to have 3 p orbitals to hold them all. And in total, I'm going to hold 6 electrons in those 3 p orbitals. If we look at D, right here, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons across a D sublevel. If we have 10 electrons, and again, only 2 electrons per orbital, that means we're going to need 5 orbitals to hold them all. And grand total, we're going to have 10 electrons in those orbitals. And if we look at F down here at the bottom, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And again, 2 electrons per orbital. If we have 14 electrons, that means we're going to need 7 orbitals to hold them. And grand total, again, 14 electrons in the F sublevel. So kind of how does this all get put together? Because I think when I teach, I've found when I teach this, you kind of tell about each thing, you tell about the energy levels, the sublevels, and the orbitals, and it doesn't quite make sense until you actually do it. And so that's what we're going to actually try now. We're going to actually start putting this together in electron configuration. And this is what electron configuration actually ends up looking like. And this is essentially the entire periodic table laid out in electron configuration, which I've never actually written all the way out. That's pretty fabulous. And I like to read the periodic table like a book when you're doing this. So if you're reading it 1s2, you start at energy level 1, and then you've got your sublevel S, and then how many electrons are there. So I'm going to go to the next slide and kind of break this down a little bit further, and then we're going to actually do an example. And I think once you do an example, this all makes a lot more sense. Okay, so when we're doing our electron configuration and our orbital diagrams, all that we're doing is using a method that's representing the arrangement of the electrons in an atom. It gives us a tool for what it looks like and how we can use it. And we have 3 rules when we're doing this: the Aufbau Principle, the Pauli exclusion principle, and Hund's rule. We're going to talk about each of these individually. The Aufbau Principle. Aufbau comes from the German verb aufbauen, which means to build up, which is going to directly correlate to what the rule means. So the electrons must enter the orbitals of the lowest energy level first. So remember we talked about there's 1, 2, 3, 4, 5, 6, so on and so forth. I can't just decide to take an electron and stick it at energy level 5. If I've got space available in energy level 1, I have to start there. Then if I've got space available in energy level 2, I have to start there. You can't just skip. And the Aufbau order lists the orbitals from lowest to highest energy. And again, that's right here. So when we're looking at this, you're probably looking at this and going, okay, what does this all mean? This looks like, Greek. It's actually very specific and very ordered, and it makes a lot of sense. So we talked about the 3 ways that we organize the electrons. The most broad was the energy level. That's this big number here. So energy level 1, energy level 2, energy level 3, 4, 3. We'll explain that part in a second. 4, 5, and so on. Then the letter is going to be your sublevel. So if you can kind of see back up here, you've got S, you've got P's, you've got D's, and you've got F's down here. And then the little number right here is going to be the number of electrons that you actually have inside that sublevel. The next rule is your Pauli exclusion principle. An atomic orbital may hold at most 2 electrons, which we talked about already. That is very, very important. And they must have opposite spins. We call them paired spins. So what does this look like? If we are drawing it out, you would draw your orbital, and you can draw it as a box. And I've often just drawn it as a line like that. Then you have to have 2 electrons in there, but they can't spin the same way. So you can't draw 2 electrons like this. That is wrong. If you draw an orbital and you draw 2 electrons in there, and I'm doing in red, sorry, you have to go 1 up and 1 down. And that is correct. So they have to have 2 electrons in the orbital, and they have to be spinning in opposite directions. And I do my arrows with a half arrow, but you could also, in theory, draw them like that. The last rule is Hund's rule. And this rule seems to make a lot of sense when I explain it like the kindergarten analogy is what I call it. But if you're in kindergarten and you've got a kid who brings candy to school, and he gives candy out to his class, and he gives Joey 2 pieces of candy, and then Susie 1 piece of candy, and then someone else another piece of candy, people would start thinking it was unfair if people were getting different numbers of candy. The way he has to hand out the candy is 1 to Joey, 1 to Susie, 1 to Nicholas, 1 to Jenny. Then once everybody has 1, then he can double up. That's what Hund's rule is. When electrons occupy orbitals of equal energy, such as the 3p orbitals, for example, 1 electron enters each orbital until all the orbitals contain 1 electron. So if you are filling this up, say we've got 1, 2, 3, 4, 5 electrons to put onto the second energy level. You fill up the s orbital, so we put 1 here, then 1 here. Then when we're filling up, we got 3 more. If we fill up the second energy level, or the second energy level, the p sublevel, you put 1 in the first, 1 in the second, 1 in the third. You cannot fill it like this. 1, 2, 3. That is incorrect. Okay, you have to fill them 1 at a time. Second electrons that you add have to be paired, and remember, they have to be spinning in the opposite direction when you notate it, as shown down here in this box. So remember, before we do one, the energy level is the number, your sublevel or your block is the letter, and then this is how many electrons that you're putting there. And again, this is all going to make sense once you actually do one electron configuration. So let's write the electron configuration for carbon. So I'm going to come down here and find carbon on my periodic table. And I like to read it like a book. So I'm going to start here. And you're going to read left to right. So the first energy level that we're on is energy level 1. And the first block that we're starting in is the S block, so 1s. And there are 1, 2 electrons there. So in 1s, we have 2 electrons. Then we keep reading. We go to the second energy level. So we've got the second energy level. We're in the S block, and we've got 1, 2. So I'm going to have 2 electrons there. Then we come across the periodic table over here to the P block, and we've got 1, 2 electrons to get to carbon. So I'm still on energy level 2, but now I'm in the P block, and to get to carbon, I've got 2 electrons left. Note that when you add up these numbers right here, 1, 2, 3, 4, 5, 6, it equals 6 electrons, which is exactly how many electrons a neutral atom of carbon has. So go ahead and pause the video and see if you can work out fluorine. Okay, so let's work out fluorine together. So we're going to start, same place, we start in 1, and then we have 2 electrons, 1s2 in the S block. Then we go to the second energy level, so energy level 2 in the S block, 1, 2. Then we go over to the P block, so it's going to be still energy level 2, but now we're in the P block, and to get to fluorine, it's 1, 2, 3, 4, 5. So we have 5 electrons. If we were going to do magnesium, you could actually, you know that magnesium is 1, 2, 3 electrons further away from fluorine. So most of this is actually going to stay the same. We're still going to start with 1s2. Then we go to the second energy level. We've got 2 in the second energy level, S block. Then we come over to energy level 2, P block, and we've got 2p. We're going to go all the way across with 1, 2, 3, 4, 5, 6 this time, because we're trying to make it down here to energy level 3. So we've got energy level 3. We're in the S block, and there's 1, 2 electrons there, so it's 3s2. And if you were going to do argon, argon would be 1s2, 2s2, 2p6, 3s2. Then we continue over here. We have to go further than magnesium because we're going to argon. We're still on the third energy level. Now we're in the P block, and we're going to have 6 electrons, 1, 2, 3, 4, 5, 6 to get to argon. So go ahead and use your periodic table and see if you can go backwards. If I give you the electron configuration, can you come up with the element that it's representing? Okay, let's look at it. So for the first one, we've got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. Follow that like a roadmap. Take it one step at a time and follow it down. So 1s2, so we've got 1s, so 1, 2. Then 2s2, 2s2, 2p6, so we're in 2p down here, 1, 2, 3, 4, 5, 6. Then 3s2, 1, 2, 3p6, 1, 2, 3, 4, 5, 6, and 3p. Then 4s2, 1, 2. Then note, it goes back to energy level 3. D is always going to be minus 1. That is actually going to be 1 energy level lower than where it seems like it is on the periodic table. So this is energy level 4, and this is energy level 4, but right here in the middle, this is energy level 3. So if we end up at 3d3, that's 1, 2, 3, and this is going to be vanadium. Number 2, if we're starting at, we've got 1s2, then we do 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, so we go all the way across down to here, 4p6 right here through there, 5s2, 1, 2, and then 4d9, so 1, 2, 3, 4, 5, 6, 7, 8, 9, and that's going to be silver. And the last one, we've got 1s2, 2s2, 2p6, 3s2, 3p6, and that ends with argon. If you were going to draw this with an orbital diagram, so for example, we wanted to draw carbon. Remember, carbon is right here. So instead of writing it out with electron configuration, we're actually going to draw it. So 1s2, so I'm going to draw my orbital, and I draw the line. You can draw a box as well, but 1s is my first sublevel, my first orbital, and I'm going to have 1, 2 electrons in it. So 1, 2. Then I'm going to go down to 2s, so 2s, and I have 1, 2. Then I go over to 2p, 1, 2, 3. Remember, I have to have 3 orbitals in order to accommodate all 6 electrons that I have in the p block. And I've got 1, 2 that I'm going to place there. Those 2 cannot be placed in the same orbital because remember Hund's rule, you have to pass out the candy to one kid at a time until everyone has one. So we're going to start here. We're going to have 1 and then 2. If you're going to do fluorine, fluorine would actually start the same way. You'd have 1s with 2 in there. Then you'd have 2s. Then you're going to have 2p. And sorry, this was supposed to say 2p up there. So then you're going to have 2p. And to get all the way to fluorine, which is right here, we've got 1, 2, 3, 4, 5. So I'm going to go 1, 2, 3, 4, 5. Note that I followed Hund's rule. I also followed the Aufbau, and I followed Pauli. All of them are spinning opposite directions. I filled from the lowest energy level up, and I didn't start refilling or putting my second electron in until I filled all of them. Magnesium would be 1s, 2s, 2p, 1, 2, 3, 4, 5, 6, and then we go down to 3, or up to 3s here. And I'm going to do 1, 2 to get to magnesium. And I raised it up because it went up in energy level because I'm used to that, but you don't have to. And if we were going to do argon, we'd have 1s, 2s, 2p has 3, 1, 2, 3, 4, 5, 6, then 3s, it's 1, 2, and we're going to argon, which is going to go into 3p, and we have 6 in there. So 1, 2, 3, 4, 5, and 6, just like that. Noble gas configuration. Some elements have very large numbers of electrons. If you go down to the lanthanides and the actinides and the lower D levels, it's just going to get really crazy. So we use noble gas configuration as a shorthand. Yay! We're really excited about that. It basically cuts out a whole amount of work for you. So what you're going to do is you're going to use the noble gas, which is in group 18, in the period above the element that you're trying to write for its noble gas configuration. So, for example, if we were going to pick strontium right here, so strontium can be found way down here. It would be a real pain in the neck to write 38 electrons out. I mean, this is what you'd have to write, and it would take a while. You can do it pretty easily, but it would take, take a valuable time. So what we're going to do is we're going to look at the noble gas that is in, the way I would put it, look at the noble gas that's right before it if you were still following down the electron configuration. So the last noble gas that your electron count passed through is going to be krypton. So we're just going to write krypton. What that's saying when we put that in notation like that is implied. All of this in the red is actually there. That's what we're implying. So then all we have to write is what's left after krypton, which is 5s12. Like that. So go ahead and pause it and see if you can do the next two elements. All right, so let's look at silver. So silver, if you're going to take all of this and make this the electron or the noble gas configuration, it ends at 4p6, which is also krypton, luckily. And then you've got 5s2, 4d9, which would take you right to silver right here. And then bismuth is the same way, except that this time you're going down to 5p6, which is actually going to be xenon. And what you're left over with on your way to getting to bismuth here, so you've got to account for all of these electrons to get to bismuth, is going to be 6s2, 4f14, 5d10, 6p3. Apologies for my bad handwriting there. And that is all I have for you. Yay! Hopefully that makes sense. Please write down any questions that you have. Make sure you go over your notes, replay any part of the video that didn't make sense, and we will go over the rest of it in class. Thanks, y'all. Hopefully it wasn't too spastic.